Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. Beneath our feet lies a planet in constant motion, a living, breathing entity whose surface is composed of massive fragments engaged in an eternal dance of creation and destruction. These fragments, Earth's tectonic plates, move imperceptibly to human perception, but dramatically shape our world over geological timescales. Each centimeter of annual movement, accumulated over millions of years, gives rise to our planet's most awe-inspiring features: mountain ranges that scrape the sky. Earth's restless nature wasn't always understood. For centuries, mountains were thought to be static features, perhaps remnants of biblical floods or primordial formations dating back to Earth's earliest days. It wasn't until the 20th century that the true mechanism behind mountain building began to emerge from scientific investigation. German meteorologist Alfred Wegener proposed his theory of continental drift in 1915, suggesting that continents moved across Earth's surface. His evidence included matching coastlines, similar fossil records, and corresponding rock formations on separate continents. Despite compelling observations, Wegener's theory lacked a viable mechanism to explain how massive continents could plow through oceanic crust. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The puzzle's missing pieces fell into place in the 1960s, with the discovery of seafloor spreading at mid-ocean ridges. Geologists found that new oceanic crust forms as magma rises and solidifies along these underwater mountain chains, pushing older crust outward like a conveyor belt. This revelation, coupled with the identification of magnetic striping in ocean floor rocks, preserving a record of Earth's periodic magnetic field reversals, provided the mechanism Wegener's theory had lacked. Thus, the theory of plate tectonics was born, revolutionizing our understanding of Earth's dynamic nature. We now know our planet's lithosphere, the rigid outer shell composed of the crust and uppermost mantle, is fractured into approximately 20 major and minor plates. These plates float atop the asthenosphere, a more plastic layer of the upper mantle, where rocks flow like an extremely viscous fluid, allowing plate movement. The driving force behind this planetary machinery is the convective flow of heat from Earth's interior. Much like a pot of boiling water, hotter material from deep within rises while cooler material sinks. This convection current system transfers heat from Earth's core to its surface, powering the endless movement of tectonic plates. As plates interact along their boundaries, three primary types of boundaries emerge: divergent boundaries where plates move apart, convergent boundaries where plates collide, and transform boundaries where plates slide horizontally past each other. Each boundary type creates distinctive geological features, but mountain building, or orogeny, occurs most dramatically at convergent boundaries. Here, as inexorable forces push massive plates together at rates of just a few centimeters per year, phenomenal pressures build. Continental crust, too buoyant to be forced downward into the mantle, instead crumples like the hood of a car in slow-motion collision. Rock that once lay flat begins to fold and fracture, pushed upward against gravity's pull. Sedimentary layers that formed in ancient seabeds can eventually reach elevations of thousands of meters through this process, carrying fossilized marine creatures to improbable alpine heights. This geological drama unfolds across millions of years, beyond the span of human lifetimes or even civilizations, yet through scientific investigation, we can read the story written in stone, revealing Earth's restless nature and the magnificent structures born from its perpetual motion. The physics behind mountain formation operates on scales so massive and time frames so vast that they challenge human comprehension. Yet underlying these grand processes are principles that can be understood through careful examination. To create mountains, tremendous forces must overcome both gravity and the strength of Earth's crust, lifting rocks against their natural tendency to remain at lower potential energy states. The process begins with stress, the force per unit area applied, to Earth's crust. Tectonic plates move at speeds averaging 5 centimeters per year, comparable to the growth rate of human fingernails. While this pace seems glacial by human standards, plates carry the momentum of continental masses, weighing trillions of tons. When these forces encounter resistance, stress accumulates along plate boundaries. 3 fundamental types of stress shape mountain ranges: compressional stress, where forces push toward each other; tensional stress, where forces pull apart; and shear stress, where forces slide past each other in parallel but opposite directions. Mountain building primarily results from compression, though the other stress types play supporting roles in specific contexts. As plates converge, rocks initially respond elastically, storing energy like a compressed spring. But rock elasticity has limits. When stress exceeds the elastic threshold, rocks either deform plastically or fracture. The behavior depends on several factors: rock type, temperature, pressure, and strain rate. Deeper, hotter rocks tend toward plastic deformation, folding like clay. Shallower, cooler rocks become brittle, breaking along fault lines. The immense pressure at convergent boundaries transforms ordinary rock through metamorphism. Heat and pressure rearrange mineral structures, creating gneiss from granite, marble from limestone, and slate from shale. These metamorphic rocks often form the cores of major mountain ranges, their distorted patterns recording the intense forces that shaped them. Mountain building isn't merely vertical uplift. Compression causes significant horizontal shortening of the crust. The Himalayas represent approximately 2,000 kilometers of Indian continental crust, compressed into a range spanning only 500 kilometers, a 75% reduction in horizontal extent. This compression manifests in extensive folding and thrust faulting. Thrust faults represent a key mechanism in orogeny. These low-angle faults allow older, deeper rocks to move upward and over younger rocks. Often, multiple thrust faults stack like shingles on a roof, creating imbricate structures that efficiently accommodate crustal shortening while building elevation. The Canadian Rockies exemplify this process beautifully, with ancient Paleozoic rocks thrust over younger Mesozoic layers. Mountains don't rise indefinitely. Isostasy, the gravitational equilibrium between Earth's crust and mantle, limits their height. Just as an iceberg's visible portion represents only a fraction of its mass, mountains have deep roots extending into the mantle. As mountains gain height, their increasing mass pushes these roots deeper until reaching isostatic equilibrium. This principle explains why Earth's highest mountains approach similar maximum elevations despite varying ages and formation processes. The weight of mountain ranges causes the lithosphere to flex, creating foreland basins adjacent to mountain belts. These basins collect sediments eroded from the rising mountains, preserving a stratigraphic record of mountain-building events. Over time, these sediments may themselves be incorporated into the mountain range through continued compression. Mountain building involves timescales far beyond human experience. The Alps began forming approximately 35 million years ago, when the African plate collided with the Eurasian plate. This collision continues today, with GPS measurements revealing ongoing convergence at rates of less than 1 centimeter per year. Despite this seemingly slow pace, the forces involved are colossal, enough to lift the weight of entire continents against gravity's pull. When continents collide, the result is Earth's most spectacular mountain ranges. Continental-continental convergence represents the most dramatic mountain-building scenario, creating ranges like the Himalayas, Alps, and Appalachians. Unlike oceanic crust, which can be subducted into the mantle, continental crust possesses inherent buoyancy that resists downward movement. When two continental masses meet, neither can easily descend beneath the other, resulting in a massive crustal pileup. Affinds. Himalayan-Tibetan system stands as the quintessential example of continental collision. Approximately 50 million years ago, the Indian subcontinent, having separated from the southern supercontinent Gondwana, completed its northward journey across the ancient Tethys Ocean and collided with Eurasia. This collision continues today, with India advancing northward at approximately 4 centimeters per year. The collision's violence transformed the landscape. The Tethys Ocean disappeared as its seafloor sediments were scraped off and incorporated into an emerging accretionary wedge. These former marine deposits now form many of the Himalayas' sedimentary sequences, evidenced by fossilized marine creatures found at elevations exceeding 8,000 meters on Mount Everest. As collision progressed, 3 major thrust systems developed, allowing older rocks to move southward over younger formations. The main central thrust pushed high-grade metamorphic rocks of the Greater Himalayan sequence over lower-grade metamorphics. The main boundary thrust moved these combined units over the youngest rocks of the sub-Himalayan sequence. Finally, the main frontal thrust marks the southern boundary where the mountains meet the Ganges Plain. The tremendous crustal thickening beneath the Tibetan Plateau represents another collision consequence. Here, continental crust reaches thicknesses of 70 kilometers, more than twice normal continental thickness. This thickening generated enormous heat from radioactive decay within the crust, partially melting deeper rocks and creating the region's granitic intrusions. The Himalayas illustrate several key principles of continental collision. First, the principle of inherited structures. Pre-existing weaknesses in the crust determine where deformation concentrates. Second, the principle of crustal shortening. The Indian plate's crust has shortened by approximately 2,000 kilometers during collision. Third, the principle of isostatic compensation. As the crust thickened, its base pushed deeper into the mantle, maintaining gravitational equilibrium. Continental collisions also create distinctive rock assemblages: high pressure, low temperature. Metamorphic rocks like blueschist and eclogite form when continental margin rocks briefly descend to great depths before being tectonically uplifted. Ultra-high pressure metamorphic rocks containing coesite and even micro-diamonds, minerals requiring pressures equivalent to depths exceeding 100 kilometers, reveal the extreme conditions these rocks experienced. The Alps formed through a more complex collision involving multiple microplates. Beginning in the late Cretaceous period, approximately 100 million years ago, the African plate began converging with Eurasia. Between them lay several microplates that were progressively consumed in a series of collisional events. This complexity created the Alps' notable nappy structures, sheet-like bodies of rock that have been thrust horizontally over neighboring formations. Not all continental collisions remain active. The Appalachian Mountains represent an ancient collision zone formed during the assembly of the supercontinent Pangaea. Between 440 and 300 million years ago, the closing of the Iapetus Ocean brought ancestral North America into collision with ancestral Africa. Although erosion has reduced their height, the Appalachians' folded and faulted structures preserve evidence of their catastrophic origins. Continental collisions eventually cease when convergent movement stops or shifts elsewhere. However, their legacy remains for hundreds of millions of years in the form of mountain ranges that, even as they erode, continue to influence climate, hydrology, and life on Earth's surface. Where oceanic and continental plates converge, a different mountain-building drama unfolds. Oceanic lithosphere, dense and thin, slides beneath the more buoyant continental plate in the process of subduction. As the descending slab reaches depths of approximately 100 kilometers, conditions trigger partial melting of the mantle above it, generating magma that rises through the overlying plate. This process creates volcanic mountain ranges with distinctive characteristics, the spectacular volcanic arcs that rim much of the Pacific Ocean in what geologists call the Ring of Fire. The Andes Mountains exemplify subduction zone mountain building at its most impressive scale. Stretching 7,000 kilometers along South America's western edge, this range formed as the Nazca Plate subducts beneath the South American continental plate. The subduction angle varies along the range, creating regional differences in volcanic activity and mountain morphology. In the central Andes, the Altiplano Plateau rises to elevations exceeding 4,000 meters, second only to the Tibetan Plateau in height and extent. Here, subduction has driven tremendous crustal thickening through both magmatic addition from below and horizontal shortening from compressional forces. The continental crust beneath the altiplano reaches thicknesses of 70 kilometers, supporting the plateau's remarkable elevation. The Andean magmatic province demonstrates how subduction creates distinct igneous rock assemblages. Magmas generated during subduction are typically andesitic in composition, named for the Andes themselves. These intermediate composition magmas, containing 57 to 63% silica, produce volcanoes with explosive eruption styles, building steep-sided composite cones. The extraordinarily tall volcanoes in the Andes, including Ojos del Salado at 6,893 meters, demonstrate the tremendous elevations subduction zone volcanism can achieve. Beyond the volcanic mountains themselves, subduction creates broader topographic effects. As the descending plate bends downward, it often creates a depression parallel to the continental margin, the Forearc Basin. Beyond this, the scraping of sediments off the subducting plate creates an accretionary wedge, slowly building underwater mountain ranges that may eventually emerge as coastal mountain chains. Japan's mountain ranges offer another window into subduction zone mountain building. The Japanese islands represent a mature island arc system where subduction has persisted long enough to develop substantial crust. 4 major plates interact around Japan: the Pacific, Philippine Sea, Eurasian, and North American plates. This complex convergence creates Japan's distinctive geography, with multiple mountain ranges running parallel to the subduction trenches. Mount Fuji, Japan's iconic volcano, rises to 3,776 meters as part of the arc created by the Pacific Plate subduction beneath the Eurasian Plate. Its perfectly symmetrical cone shape represents the classic form of a stratovolcano built from alternating layers of ash, pumice, and lava flows. Subduction doesn't always create continuous volcanic chains. The Cascade Range of western North America, stretching from northern California to British Columbia, features individual stratovolcanoes spaced dozens of kilometers apart. These discrete volcanoes, including Mount Rainier, Mount St. Helens, and Mount Shasta, sit atop the older basement rocks of the North American continent, rather than forming a continuous volcanic highland. The discontinuous nature of these volcanoes relates to magma generation processes at depth. Volatiles released from the subducting Juan de Fuca plate trigger melting in the mantle wedge above, but these melting zones develop in distinct regions rather than continuously along the margin. Each major stratovolcano represents a separate, magmatic system with its own crustal magma chamber and eruptive history. Island arcs forming where oceanic plates converge with each other represent subduction's most fundamental expression. The Aleutian Islands, Mariana Islands, and Tonga Kermadec chain exemplify these systems. Their volcanic mountains, rising from the deep ocean floor, may appear modest in elevation above sea level. However, measured from their true base on the seafloor, these mountains rank among the tallest topographic features on Earth. Where tectonic plates move apart at divergent boundaries, a different style of mountain building occurs, one characterized by extension rather than compression. These divergent margins create some of Earth's most distinctive topographic features, including mid-ocean ridges and continental rift valleys. Though less visually dramatic than the towering peaks of collisional or subduction zones, these extensional features play crucial roles in Earth's evolving landscape. Mid-ocean ridges form the longest mountain ranges on Earth, extending over 60,000 kilometers through all major ocean basins. These submarine mountain chains mark constructive plate boundaries, where new oceanic crust forms as magma rises from the mantle below. The Mid-Atlantic Ridge exemplifies this process, creating a continuous submarine mountain range that snakes through the Atlantic Ocean from the Arctic to near Antarctica. As plates diverge at rates of 2 to 20 centimeters per year, the resulting extension thins the lithosphere, reducing pressure on the underlying asthenosphere. This pressure decrease triggers partial melting, generating basaltic magma that rises to fill the gap between the separating plates. The continuous influx of magma creates new oceanic crust through a process resembling a submarine assembly line. The topography of mid-ocean ridges displays a characteristic profile. a central rift valley flanked by parallel ridges that decrease in elevation with distance from the axis. This morphology results from the thermal evolution of oceanic lithosphere. Newly formed crust at the ridge axis is hot, thin, and buoyant. As it moves away from the spreading center, the crust cools, thickens, and subsides, creating the ridge's sloping flanks. Although most mid-ocean ridges lie deep beneath the ocean surface, Iceland provides a rare opportunity to observe these processes above sea level. Iceland straddles the mid-Atlantic ridge and sits atop a mantle plume, a column of abnormally hot rock rising from the deep mantle. This combination generates exceptional volcanic activity that has built Iceland above sea level. The island's central rift valley, with its numerous fissures, normal faults, and active volcanoes, offers a window into divergent boundary processes normally hidden beneath the oceans. Continental rifting represents the early stage of divergent boundary formation before seafloor spreading begins. The East African rift system exemplifies this process, where the African continent is slowly tearing apart along a 7,000-kilometer system of rift valleys. This continental breakup has progressed furthest in the north, where the Red Sea and Gulf of Aden represent young ocean basins that have already progressed to seafloor spreading. The East African rift's topography presents a stark contrast to compressional mountain ranges. Here, the dominant structures are normal faults, where rock on one side slides downward relative to the other, rather than reverse or thrust faults. These faults create a series of down-dropped valleys, grabens, bordered by elevated shoulders, horsts. The result is a landscape of long, linear valleys flanked by steep mountain fronts that can rise several thousand meters above the valley floors. Volcanoes associated with continental rifts differ from those in compressional settings. The extensional environment allows magma to rise more easily, producing more fluid, basaltic eruptions rather than the explosive, silica-rich eruptions typical of subduction zones. The Great Shield volcanoes of East Africa, including Mount Nyiragongo, Mount Kilimanjaro, and Mount Kenya, exemplify this style of volcanism. Kilimanjaro, Africa's highest peak at 5,895 meters, began forming approximately 1 million years ago through repeated eruptions along the developing rift. The Basin and Range Province of the western United States offers another example of extensional mountain building. Here, over the past 30 million years, the North American continent has stretched like an accordion, expanding by up to 100% in an east-west direction. This extension created more than 150 mountain ranges separated by flat-bottomed valleys. Each range represents a tilted fault block, uplifted on one side and down-dropped on the other. Unlike collisional mountains, which often feature metamorphic cores exposed by compression and erosion, mountains formed by extension typically expose rocks that were previously buried within the crust. As fault blocks tilt, they reveal cross-sectional views of earlier geological formations, making these ranges valuable natural laboratories for studying crustal composition. As soon as mountains rise, opposing forces begin to tear them down. Wind, water, ice, and gravity, the agents of weathering and erosion, constantly work to return elevated land masses to base level. This perpetual conflict between tectonic uplift and erosional processes shapes mountain landscapes over millions of years, creating the distinctive features we associate with mountainous terrain. Physical weathering fractures rocks without changing their composition. In alpine environments, the freeze-thaw cycle proves particularly effective. Water seeps into rock cracks, expands approximately 9% upon freezing, and exerts pressures exceeding 2,000 kilograms per square centimeter, sufficient to split even the hardest rocks. This process, called frost wedging, gradually reduces massive bedrock to angular fragments. Chemical weathering alters rock composition through reactions with water, oxygen, and atmospheric gases. Carbonic acid, formed when carbon dioxide dissolves in rainwater, dissolves limestone mountains particularly effectively, creating karst landscapes with sinkholes, caves, and tower-like formations. In the humid tropics, chemical weathering can reduce even resistant rocks like granite to clay at rates 20 times faster than in temperate regions. Mountain streams harness gravity's power to transport weathered material downslope. These high-gradient waterways carry enormous sediment, loads during flood events, with boulders weighing several tons moved by exceptional floods. The characteristic V-shaped valleys of mountains largely result from this fluvial incision, as streams cut downward faster than slope processes can widen the valleys. Glaciation dramatically reshapes mountain landscapes during ice ages. Valley: glaciers transform V-shaped stream valleys into U-shaped troughs with flattened floors and steepened walls. Cirque glaciers carve amphitheater-like hollows at mountain heads. Where multiple cirques form back-to-back, they create knife-edge ridges, called arêtes, while the intersection of 3 or more cirques produces pointed peaks known as horns. The Matterhorn in the Swiss Alps exemplifies this glacial sculpture, its distinctive pyramid shape resulting from cirque glaciers attacking from multiple directions. Mass wasting, the gravity-driven movement of material downslope, contributes significantly to mountain erosion. Rockfalls occur when blocks detach from steep cliffs, while landslides involve the rapid movement of larger rock masses along failure plains. Debris flows, mixtures of water and sediment with the consistency of wet concrete, can transport enormous volumes of material during single events. These processes create distinctive landforms, including talus slopes, accumulations of angular rock fragments at cliff bases, and alluvial fans where mountain streams deposit sediment upon reaching flatter terrain. The balance between uplift and erosion determines a mountain range's evolution. Where tectonic forces remain active, as in the Himalayas, continued uplift maintains high elevations despite aggressive erosion. GPS measurements indicate parts of the Himalayas rise at rates approaching 1 centimeter per year, offsetting similar rates of erosional lowering. When tectonic processes cease, erosion gradually reduces mountain heights. The Appalachians, formed during Paleozoic continental collisions more than 300 million years ago, once rivaled the Himalayas in scale. Today, having endured hundreds of millions of years of erosion without significant renewal, they stand much reduced, with maximum elevations around 2,000 meters. Mountain erosion doesn't merely destroy, it redistributes. Material removed from highlands accumulates in adjacent basins, forming thick sedimentary sequences that preserve records of mountain evolution. The Ganges Plain south of the Himalayas contains sediments exceeding 6 kilometers in thickness, representing material eroded from the rising mountains during the past 20 million years. Climate plays a crucial role in determining erosion rates and mountain landscape evolution. In mid-latitude ranges like the European Alps, the most intense erosion occurs at intermediate elevations where precipitation is highest and temperatures fluctuate around freezing, maximizing frost wedging effectiveness. Higher elevations, despite steeper slopes, often experience lower erosion rates due to reduced precipitation and temperatures persistently below freezing, which limits water availability for erosional processes. As mountains erode and evolve, they display characteristic sequences of landforms. Initially, steep slopes and V-shaped valleys dominate, with frequent landslides and debris flows. Over time, valley floors widen, slopes become gentler, and relief decreases. Eventually, given sufficient time without renewed uplift, even the mightiest mountains reduce to low rolling hills, their once towering peaks surviving only as stories written in the rocks they leave behind. The grand mountain-building processes shaping our planet continue unabated in the 21st century. Tectonic forces persist at the same rates that have operated for billions of years, driving ongoing mountain formation across the globe. Today's advanced monitoring techniques, including GPS networks, INSAR satellite measurements, and seismic tomography, allow geologists to observe these processes with unprecedented precision, revealing Earth's dynamic nature in real time. In the Himalayas, the Indian subcontinent continues its northward journey, advancing at approximately 4 centimeters yearly. This ongoing collision ensures that the highest mountains on Earth continue to rise, despite intense erosion. GPS measurements confirm contemporary uplift rates approaching 1 centimeter per year in portions of the range. The devastating 2015 Nepal earthquake, which triggered massive landslides and altered the height of Mount Everest by several centimeters, demonstrated the powerful forces still at work in this collision zone. The Alpine Himalayan belt, stretching from Western Europe through the Mediterranean into Asia, remains Earth's most active continental collision zone. Recent GPS data show that Anatolia, modern Turkey, continues moving westward at rates up to 2 centimeters per year, escaping the vice-like compression between the African and Eurasian plates. This movement generates numerous earthquakes along the North Anatolian Fault, including the tragic 2023 events that claimed over 50,000 lives. Along the Pacific Rim, subduction continues to build volcanic mountain chains. The Cascades Range of Western North America experiences ongoing magmatic activity, with Mount St. Helens, Mount Rainier, and other volcanoes presenting significant hazards to surrounding communities. Since its catastrophic 1980 eruption, Mount St. Helens has undergone several dome-building episodes, demonstrating how subduction zone volcanoes continually rebuild themselves through eruptive activity. East Africa's continental rift steadily widens at rates of several millimeters per year, gradually splitting the African continent. Satellite measurements reveal that parts of the Ethiopian segment spread at rates exceeding 7 millimeters annually. Should this rifting continue, East Africa will eventually separate from the mainland, creating a new ocean basin over the next 50 million years. A glimpse into how the Atlantic Ocean began forming 180 million years ago. Climate change introduces new variables into mountain evolution. Rising global temperatures accelerate glacial retreat worldwide, removing ice masses that have shaped mountain landscapes for thousands of years. This deglaciation triggers numerous feedback effects, including reduced pressure on mountain masses that can accelerate uplift through isostatic rebound. In Alaska's St. Elias Range, glacial retreat has triggered uplift rates exceeding 3 centimeters per year in some areas, among the fastest vertical movements measured anywhere on Earth. Changing precipitation patterns affect weathering and erosion rates. Regions experiencing increased rainfall intensity see accelerated erosion and more frequent mass wasting events, while areas becoming drier may see decreased erosion rates. These climatically induced changes interact with tectonic processes in complex ways that scientists are only beginning to understand. Human activities increasingly influence mountain landscapes. Mining operations literally remove mountains, as evident in Appalachian mountaintop removal practices. Dam construction traps sediment that would otherwise travel from mountains to oceans, interrupting natural sediment transport systems developed over millions of years. Urbanization and deforestation on mountain slopes increase landslide frequency and severity. The study of mountain building continues advancing through technological innovation. Improvements in geochronology, methods for determining absolute ages of rocks and landforms, allow increasingly precise reconstruction of mountain evolution histories. Cosmogenic nuclide dating measures isotopes produced when cosmic rays strike minerals, enabling geologists to determine exactly when rock surfaces were first exposed by erosion or tectonic uplift. These techniques reveal erosion rates over timescales from thousands to millions of years. Computational advances permit increasingly sophisticated modeling of mountain building processes. Supercomputers now simulate complex interactions between tectonics, climate, and erosion over geological timescales, providing insights into how mountains evolve under various conditions. These models help predict how current mountain ranges might respond to ongoing climate change and tectonic activity. As human understanding of mountain building deepens, so does appreciation for these majestic features' role in Earth systems. Mountains influence global climate patterns, create biodiversity hotspots, supply water to billions through their glaciers and watersheds, and provide natural resources essential to human civilization. The ongoing symphony of tectonic plates continues to compose Earth's most dramatic landscapes, a performance 50 million years underway and still building toward its crescendo.